All right. I have to email. Okay. That. Cool. Hi, everybody. Justin. Hey, Meg. What's up? Ali. Siddharth. Alon. Hi. Gallagher. Alexi. Ethan. Hey, Esther. Hello, John. Okay. I haven't eaten breakfast yet. Just give me a sec. I'm going to munch on some crackers, and then we can get started with going over the solutions. Yeah? Let's get pumped. Who's pumped? Let me see some pumps in the chat. Huh? These are good. My mother sent me these. I love these crackers. Ace crackers. I know. They're like better Ritzes, I think. The less saltier versions of Ritz crackers. Do I like the square shape or the circle shape better? I don't really care. Oh my god. Thank you for the pumps, right? Pump it up. Hey Aoife, how's it going? Good morning, Labiba. I just gotta brew this pot and we can get started. I got a full 8 hours of sleep last night. Oh my heck yeah, right? But as many of you know, the real trouble you run into when you don't get enough sleep one night is not the morning after, but the next morning or the next day, right? So I'm on that second day hangover today, and it's even though I got 8 hours yesterday, I'm feeling the previous night's deficiency even more today. Right? So that's why I need some tea. I love tea. I love you. Okay. Gotta shake it around. Yeah, gosh. Oh yeah, okay. Okay, now we can begin. And what do I want to do? Let's go over from the very first worksheet. Let's see. From the very first worksheet, I want to go over number 1 and number 3. Okay? So really quickly, here's number 1. Okay? At t equals 0, I have that. At t equals 1, I have this. There is no overlap. At t equals 3, it looks like this because they are completely overlapped together. And then it looks like, and then, right, oops, this should be further out, sorry. I moved this one too far this way, and this one not enough, right? But the same concept remains, right? The top one's moving to the right, the bottom one's moving to the left, right? That's number 1. Let's talk about number 3, okay? Hey! If you did it this way, especially for this one, and showed with a third color, like what the 2 posts are doing, that's fine, right? But the important thing is, even if you show like what this one is doing and what this one is doing, like the more important thing you really want to do is to show us what the string will actually do, right? Like, even though, yeah, there is an upward pulse at this location at time equals 3, and there is an upward pulse at this location at that time, right? If you were filming this or taking a picture of the rope, how would the rope actually look like? What would it actually look like? It'd just be this flat black line at that point in time, right? So let's move on to number 3 from that worksheet, right? I think it's really interesting. We have a wide one and a short one. I mean, a wide one and a skinny one. Right? It's going to go this way. It's going to move 2 paces, 2 paces. So what you should have is like a 1 block width thing in between them because they both move 2 paces. Then in the middle, their centers are actually completely overlapped, and that looks like this, right? But this is 1, 2, 1. So in this really small 2 block wide place, I have perfect destructive interference, right? And then after that, it looks like this. Oh crap, I did it again. Well, it looks like that, right? So the only point in time where I actually have interference is at time equals 2 seconds, right? Like at this time and this time is the only time I have interference. I went over 2 examples with destructive interference because I think it's more interesting, right? But constructive interference you should have seen in the video, right? Did you guys see how like one wave was going this way and the other wave was going this way? And their overlapping part was changing the whole time, but where they overlapped, like there was like a really, really tall wave. I thought that was super cool. Excuse me. Okay, so let's keep going. I want to move on to the second worksheet, okay? And for this one, basically, for the very first one, it's perfect constructive interference. Everywhere you look, there's going to be perfectly constructive interference, right? So what you end up with for number 1 in the second sheet is just a sinusoidal wave of amplitude 2, right? Where this height is now 2 instead of 1. The second problem is exactly the opposite. Every point you pick, no matter what, should result in destructive interference. And not only is it destructive interference, it's perfect destructive interference. Like at one point in space, if the first wave has a height of like 0.3, then the other wave has a height of -3, right? -0.3. If at another point it's like positive 0.51, then the other wave will have -0.51, right? So everywhere I have destructive interference, not only that, it's perfect. So number 2 is a straight line, right? Everywhere cancels. Number 3 is exactly the same as number 1, except it now has an amplitude of 3 because there's a wave of height 2 and a wave of height 1, and everywhere I go, there are thingy things, right? Number 4 is, again, I have destructive interference everywhere, but it's not perfect, right? It's not going to completely cancel out. So it looks like, right, it just looks a height of 1, right? That's it. Good morning, Dahlia. Now, what I will leave for another homework assignment due tomorrow is just to do the rest of the sheets. Right? I wanted to pace this over 2 days. Yeah, it's ghost of a potato chip. If you did the whole thing wrong, it's all right. There's so many problems, right? There's 12 problems on the first sheet, 8 problems on the second sheet. Just do those, right? Unless you did everything, which if you did, cool, but you got to redo it, okay? All right, so let's move on. Today I really wanted to focus on not just constructive interference, but destructive interference, okay? And to do so, one of the different shaped waves, basically, if I have what if I wanted to add up these 2 waves and say, what do they look like here? Well, all you have to do is like, hey, at this point, how high or how low am I going to be? I don't know. To do that, you're going to have to look at how high am I here, how high am I here, add them up. And then you put it down here. Well, where am I here? Add that height up, and then put it there, right? And to get a really high resolution picture, you're going to have to do that at a lot of different points to really get the right shape of the wave, right? If you only do it like here and here and here, you're not going to get a really precise picture, okay? Yeah. Today we're going to be talking about, that's more homework stuff, right? Today we're going to be talking about phase. And it's the, how do I describe phase? Mr. So, you should know this, you're a teacher. Shut up, everyone's banned, okay? It's just a phase, right? It's just a phase, Mom, right? It means it's a time in your life, and it'll pass, right? So when I'm talking about a wave, right, and it's going to travel like this. This particle, this molecule is going to do the same thing over and over again, right? It's going to go down, and then up, and then down, and then up, right? So this particle, as this wave passes by, is going to do this. Whoa, 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 whoa. So it does the same thing. And whatever part of the wave it's in, we call that's the phase, right? So this part of the wave and this part of the wave represent the exact same phase, right? So when this part of the wave hits that particle is going to be that low, and then it's going to go up. And then when this part of the wave hits that particle, it'll be at the exact same height or depth that it was when that part of the wave was. So we would say it's an identical phase, right? Now, if I look at this point and this point, they're in the same phase, but this point and this point are not in the same phase, right? Because although when this part of the wave hits that particle, it's at an equilibrium height, and when this part of the wave hits that particle, it's also at the same equilibrium height. Why do we say then that they're in different phases, right? Well, I would say that because when this part of the wave hits that particle, it's on its way up, right? It's going towards that part. So the particle is moving up when it's at that part of the wave. But when it's at this part of the wave, it's pointing down. It's moving down. So it's not in the same phase, right? We most frequently, what's the unit of measurement for phase? Degrees. Right, so when we say things are like 360 or 720 degrees, these 2 points are 360 degrees away. These 2 points are also 360 degrees away. Basically like a periodic sine function. And these 2 points are 720 degrees away, right, in phase. And whenever 2 points of a wave are multiples of 360 away from each other in phase, we say they are in phase. Okay. Anything else, we say it's out of phase. Right? So these 2 points are out of phase by 180 degrees. These 2 points are out of phase by 90 degrees. Right? That's the kind of terminology we use, right? So it's the phase is the part of the cycle that a point on a wave represents. Okay. Now, if I send 2 identical waves, right? If I have one speaker here and it emits a sound wave, and I have a second speaker and it emits an identical sound wave of equal amplitude and equal frequency, then they basically add up and produce constructive interference because they're in phase. However, if I make a second speaker, if my second speaker is 180 degrees out of phase with the other speaker, right? Now I have destructive interference, right? crest corresponds with that trough corresponds with this crest, this trough corresponds with that crest, right? And 300 degrees is basically one wavelength, exactly. And this is exactly how noise-canceling headphones work, all right? So if I have my ear here, here's my ear, it's a beautiful ear, okay? And I have a headphone here. And here's a sound wave that goes into your ear. This headphone is a remarkably, okay, actually, it's ugly. So here's your ear. Here's my headphone. And here is some external noise, okay? And it goes into your ear, right? What your headphones do, right? They have a microphone, or they have some way of picking up the frequency of the wave, and then in this speaker, in addition to putting out the music, right? Here's your music, right? It also spits out an identical wave to the outside stuff, but out of phase by 180 degrees. Right? So your noise-canceling headphones puts out two sound waves, the actual music file, and then a real-time out-of-phase thing to what it perceives from the outside. Now, if you want to think about how hard that is to do, because this purple wave travels, all sound in normal air travels at 340 meters per second. So when your headphone takes in this purple wave, what's this distance? Or actually, what's this distance? Right? That's like 2 centimeters, right? So if velocity is distance over time, and I have 340 equals 0.02 over the time, my time is, oh my goodness, I have that much time. 0.00, maybe, you get the gist, right? It's like a really small amount of, from the time this purple wave hits here, and from the time it's here, my headphone needs to be able to calculate and generate the opposite wave to cancel. And that's exactly what it does. Whoa. Yes, Alon, the point remains, Alon, okay? It's a small amount of time. Yeah, that's why I talked about the width of the headphone rather than this. That's why I changed that, right? And that's like a remarkable feat of engineering, how that happens, I think. It's a pretty cool mechanism if you're interested in like how that actually works. But yeah, that's how noise canceling headphones works. It inputs an external wave and outputs an identical wave, but 180 degrees out of phase, and it cancels. But not only that, it has to be of equal magnitude, right? Because if this is the wave it wants to cancel out, and it puts out a wave 100 degrees out of phase, but not of, so this orange wave is now 180 degrees out of phase with the purple wave, but it won't perfectly destructively interfere, right? Because in order to perfectly destructively interfere, it needs to have an equal amplitude, right? So this is basically the difference between number 2 and number 4 from the second sheet of the homework, right? like I can have destructive interference and not perfectly cancel it out, right? In order to perfectly cancel it out, I need to be both 180 degrees out of phase and also of equal amplitude, or else it won't perfectly cancel out. How is that even possible? Modern engineering, Dahlia. It's very possible. All right. That's all I'll leave you with today. Really short lesson. Please do the rest of the worksheet. I think it's really important if you really want to understand how interference works. Interference has so many applications, right? It's not only explaining how noise canceling headphones work. We're gonna use it to talk about how musical instruments work, like guitars and violins and cellos. And we're also gonna talk about do I have the thing with me right now? I do not. All right, but we're also going to talk about how interference is used to make music harmonically and how chords are developed and stuff. All right. All right. So have a great day. See ya.